Okay, so this is Dr. Sarah Horst. She got her undergraduate degree, assuming a double major in planetary science with honors and literature with honors from the California Institute of Technology. And then she went on to get her PhD of planetary science at the University of Arizona in Tucson. And she's going to give a talk on Titan as prebiotic chemical systems. So if you want to go ahead.
Okay, so let's see. I'm going to talk about Titan. So this picture on this slide is Titan, as you may have guessed. So before I do anything else, though, there are some formalities you always have to do when you do these kinds of things. Okay, there we go. So I just quickly need to acknowledge some collaborators on some of the work that I'm going to talk about today. There's a big whole list of them. You can see that what we do in planetary science covers lots of different universities, and there's a couple of continents represented there, so lots of collaborators. In particular, I just want to thank Maggie Tolbert at the University of Colorado and Roger Yell at the University of Arizona. Also, just to acknowledge our entire research group here at the University of Colorado, the Tolbert Group, and also my current funding source, which is the National Science Foundation. One more thing, I am only going to be here in Colorado for a few more months. I am actually moving to Baltimore. I'm going to be starting as an assistant professor at Johns Hopkins next fall. It's not just me, it's also Kevin Lewis, who is a Martian geologist. So there's going to be a lot of opportunities for grad students and postdocs who are interested in planetary science. So if you have any interest in coming to work with us, there's email addresses right there. Feel free to contact either one of us about what kinds of opportunities there might be. So with all that out of the way, I'm going to give you a quick introduction to Titan. So Titan is the largest moon of Saturn. Its diameter is about 5150 kilometers, which makes it actually the second largest moon in our solar system. So the only moon that's larger than Titan is Ganymede, which is the largest moon of Jupiter. And actually, Titan is larger than the planet Mercury, so it's a fairly substantial body in our solar system. It was discovered by Cassini-Huygens in 1655, so we've known about Titan for quite some time. And it's kind of hard to do this without a laser pointer, but Titan's actually in this image. So obviously you can see Saturn quite well, but Titan is kind of down in the bottom right of the image. So Titan also has a mass of about 0.0225 Earth masses. So that means that Titan has a density of about 1.9 grams per centimeter cube. So something like that in our solar system means that it's probably about half rock, half water ice. The density of water ice is around 1. The density of rock is around 3. So something with a density of 2 is about half and half. And so we consider it to be an icy body in our solar system, not kind of a rocky planet like you would think of Earth or Mars. The surface temperature on Titan is about 94 Kelvin, which is very, very, very cold. In fact, water ice at 94 Kelvin behaves more like granite than like ice. And so that's something else that we have to consider when we're studying Titan. And finally, and most importantly for a lot of what I'm going to talk about today, Titan's the only moon in our solar system that has a substantial atmosphere. And so that's one of the reasons that we find it so interesting. And I'm going to talk about the atmosphere more in a little bit. Just to give you a sense of kind of size comparisons, as I had mentioned, Titan is the second largest moon in our solar system. Ganymede's only just a little bit bigger, and actually for a long time we didn't know where Titan's solid surface was because it does have this thick atmosphere. And so for actually many, many years, we thought that Titan was the largest moon in the solar system. It was only once we were able to find out the solid surface radius that we discovered, in fact, it was not the largest moon. You can see compared to Mercury, and then also Callisto and Io are both on there. Those are two moons of Jupiter. You can see our own moon down there, which is actually quite small compared to Titan. And then Europa is just a little bit smaller than that, which is the other large moon of Jupiter. And then just to give you a size comparison to our own system, so this is Titan in the middle compared to Earth and compared to the Moon. So it's a bit bigger than the Moon, but still a fair amount smaller than our own planet. So I'm going to talk a little bit about Titan's atmosphere now, just to give you some background. So Titan's atmosphere is actually quite dense. The surface pressure is about 1.5 bar. So the surface pressure at sea level on Earth is 1 bar. So there's actually, the atmosphere is actually more dense on Titan than it is here on Earth. And Titan's atmosphere is made out of about 98% molecular nitrogen and 2% methane. So right away, one of the reasons that we think that Titan is so interesting is because this is actually the only other the only other thick atmosphere in our solar system that is mostly molecular nitrogen besides our own atmosphere. And so one of the things that we tend to say about Titan is that we like to think of it as an analog of the early Earth. So Earth's atmosphere only has oxygen, which is the other main component, because of life on Earth. So early in Earth's history, before there was life, Earth's atmosphere was almost certainly mostly molecular nitrogen. And so we kind of like to study Titan as a bit colder analog of what the early Earth may have been like, and hope that by studying Titan we can learn more about processes that occurred many, many billions of years ago in Earth's history. The other main component of Titan's atmosphere is methane, so there's about 2% methane. And so what happens in Titan's atmosphere, and I'll walk through this a little bit more later on, is that we have photochemistry in Titan's atmosphere. And so what happens is that solar photons and also energetic particles that come from Saturn, from Saturn's magnetosphere, and also from the solar wind, will come into Titan's atmosphere. They run into a nitrogen molecule or they run into a methane molecule, and they can break that molecule. They have enough energy to break those bonds. And so that then starts a process where some of the fragments of nitrogen and methane will start to react with each other, and we can build more and more complex molecules, molecules that we call hydrocarbons, and I'll talk a lot more about those later, and also nitriles, which have nitrogen in them. And so Titan ends up with this very complex organic chemistry occurring in its atmosphere, and that just doesn't happen with gases, but also we have gas-based chemistry that eventually leads to the formation of particles. And so we can have haze particles form. And so you can see in this picture, and in some of the pictures I've already shown, the Titan's atmosphere is very hazy. It's kind of reminiscent of maybe Los Angeles. We actually, here in the Denver Boulder area, have something that we call the Denver brown cloud, which is a haze that forms from photochemistry of automobile exhaust. And so we get kind of similar processes going on in Titan's atmosphere that form this haze. And the haze has kind of two parts, which I'll talk about a little bit more in a bit. So we have something called the main haze layer, which in this picture kind of shows up as that brownish, yellowish, orangish area that you can see covers the whole planet. Actually, this image is backlit, and so you can't see it as well. But the other part, which is why I picked this picture, is we also have something called the detached haze layer, which is that ring that you can kind of see around in the image. And so it's another thing that we're trying to understand are these processes. One thing to know about the detached haze layer, that ring that you can see in this image is about 400 kilometers from the surface, just to give you a sense of scale. And one other thing to point out that's kind of interesting, though we don't understand it at all right now, is if you look at the bottom of the image of Titan that I'm showing here, there's kind of a fuzzy brown blob, I guess is the best way to describe it, at the bottom of the image. And that's right near the South Pole. That is a vortex that started forming sometime last year, and we're still trying to understand what it is and what exactly it's doing there, but we've been able to watch that in real time over the last year, and so that's been kind of interesting too. So one of the other things to know about Titan is that its atmosphere is pretty reducing, so that just means that there's not a lot of oxygen in the atmosphere. But there are some oxygen-containing molecules. There's 3 that have been detected, so carbon monoxide, carbon dioxide, and water are the 3 that have been detected. Of those, carbon monoxide is the most abundant. It has an abundance of about 50 parts per million. And so that doesn't sound like very much, but in fact, that makes it the fourth most abundant molecule in Titan's atmosphere. And so kind of taking all of those pieces together, one of the reasons that Titan's atmosphere is very unique in our solar system is that it is reducing. It doesn't have a lot of oxygen, but there is some. And so if you kind of look on the gradient of atmospheres in our solar system, we have Earth, for example, which is very oxidized atmosphere compared to everybody else. Mars is actually also a very oxidized atmosphere. Most of the other atmospheres in our solar system are very much the other direction. So things like Jupiter and Saturn, Uranus and Neptune, they have tons and tons of hydrogen in their atmospheres, and so they're very reducing. So Titan is kind of this in-between case, and that leads to the possibility for a lot of really interesting chemistry to be occurring. And one of the reasons that we're so interested in this chemistry is that life as we know it, so life on Earth, is built kind of a small set of molecules that are common to every organism that we find on Earth. And those molecules are all built out of carbon, nitrogen, hydrogen, and oxygen. And so one of the things that we're interested in trying to learn is what kinds of chemistry can occur in atmospheres and what kinds of things can we build from these molecules. So how do we study Titan? So we've known about Titan's atmosphere potentially since the early 1900s. This is a drawing because of the period of time that was made by the first person who claimed to be able to see Titan's atmosphere. And there's been a lot of discussion since over the past, I guess, 10 years about whether or not this person actually discovered Titan's atmosphere. The size telescope that they were using probably was not sufficient to be able to detect what we call limb darkening, which is how you would tell that there was an atmosphere around Titan. But at the same time, the person who made the detection or claimed to make the detection was well known to have very good eyesight. And there was the period of time in astronomical history when having good eyesight could actually mean the difference between discovering something and not discovering something. So it's possible that he did detect it. Whether or not he found it, in the mid-1940s, Gerard Kuiper discovered methane around Titan's atmosphere. And so that was kind of our smoking gun to know that Titan had an atmosphere, was this discovery of methane around Titan's atmosphere. But that was pretty much all we knew about Titan until the early 1980s. So this was our first up-close picture of Titan. This was taken by the Voyager 1 spacecraft. And you can see that Titan kind of torments scientists. So you will hear people refer to Titan a lot as an enigma. And this is kind of one of the reasons, just from the very beginning of our exploration of Titan, it's always been very guarded with its secrets. And so as Voyager 1 flew by, it returned these images, and what we found out was that Titan was an orange fuzzy ball, that the haze in its atmosphere is so thick that we couldn't see down to the surface at all. If there had been little green men or little blue women or little brown creatures standing on the surface waving at us, we wouldn't have known because of the atmosphere. And so it was very frustrating to scientists to not be able to find out very much. But we did find out one thing. Voyager was carrying an instrument called an infrared spectrograph. And so this is an instrument that looks at infrared light. And from this instrument, we were able to find out that there is complex organic chemistry occurring in Titan's atmosphere. This was something I had mentioned earlier. And so from Voyager, we found out that there are molecules like propane, like you use for your barbecue, acetylene, ethane, hydrogen cyanide, which is highly toxic. And all of these molecules gave us an indication that very complex organic chemistry was occurring in Titan's atmosphere. And so, of course, coupled with the fact that we had absolutely no idea what the surface looked like or what was there, of course, our instant reaction, our gut reaction, was that we had to go back as soon as we possibly could. That ended up not being very soon. So, like I said, this was the early 1980s, probably. Well, this was actually before I was born, which means it was certainly before all of you were born. So our next kind of step in exploration is something called Cassini-Huygens. So did it die? Where'd my slide go? That's not good. Can you guys see my slide? Oh, there it is. Okay, so Cassini-Huygens is a joint NASA-ESA mission. It launched in 1997, so you can see it took about 16 years between the Voyager flyby of Titan of the Saturn system and being able to build and launch another spacecraft. But it takes a really long time to get to the outer solar system, so it took 7 years from when Cassini launched until it arrived at the Saturn system, so it was 7 years in what we call cruise. Cassini also carried a probe called Huygens, which was a probe to study Titan's atmosphere that was dropped onto Titan, landing in 2005, early 2005. The picture that's shown here is a picture of Cassini and Huygens as they were being prepped for launch. That kind of giant giant gold circle right there is the heat shield from Huygens. So that was the probe that was released. One thing that I realized recently that I have to point out when I show people this picture is that there's actually those little white things at the bottom of the spacecraft are people. So Cassini is huyge. It's about the size of a school bus and carries with it a number of instruments. So Cassini has 12 different instruments. Huygens had 6, and those instruments are meant to characterize a wide variety of things. This mission wasn't just a mission to Titan, it's to study the entire Saturn system, and so it has to have instruments to be able to characterize Saturn, Titan, the other icy moons of Saturn, the plasma environment, magnetic fields, all of those things. There are instruments that are specifically designed to be able to study those things on the spacecraft. And the spacecraft is still operational, so we've now been in orbit around Saturn for almost 10 years. Hopefully, although it depends very much right now on funding situations, the mission will continue until 2017. No matter what, the mission will end in 2017, and it will end with Cassini crashing into Saturn. We have to be very careful when we send spacecraft places in our solar system that we don't contaminate places that we think could potentially host life, and so in an attempt to protect the icy moons in the Saturn system which might harbor life, we have to make sure that the spacecraft doesn't end up there, and so it will crash into Saturn, hopefully in 2017 if we have money to go that long. Otherwise it'll be sooner. That is a discussion that's ongoing right now with NASA. So this is Cassini sitting on the launch pad, and then I always have to show the gratuitous launch picture, and so here was Cassini the night that she launched in 1997. So what have we learned from Cassini? So I'm going to step through a couple of things that we've learned about Titan from Cassini, and in particular I'm going to focus on the chemical environments. The title of my talk was Titan as a Prebiotic Chemical System, and so we're not just interested in the chemistry that's occurring in the atmosphere, although that's mostly what I study, but we're also interested in the body as a system and how the different pieces might interact to form an environment that might be either hospitable for life now or could potentially at least have processes that could lead to life at some point. So this is our orange fuzzy ball picture from Cassini. So $3.5 billion later, this is what we get. It's much higher resolution than the Voyager image. So we've learned a lot about a number of different environments. So for example, we know a lot more about the haze in Titan's atmosphere than we used to. So this is an image of the haze. You can see that there's quite a bit of structure. Probably a lot of that comes from waves in Titan's atmosphere. We have an idea now that the haze is probably mostly made out of hydrocarbons, which are molecules that are just made of carbon and hydrogen, so things like propane, nitriles, which have a carbon and a nitrogen in them, amines, which are nitrogen and hydrogen containing compounds, things like ammonia, and then aromatics, which are molecules that have a ring, so things like benzene. So we know that there's a lot of complex organic molecules in the haze itself. the Huygens probe also carried a number of instruments which were specifically designed to characterize the haze, and so we know a lot more about the way that it scatters light, and we know that the haze particles are probably fractal aggregates, which is very interesting. And then we also have been able to study in more detail the clouds in Titan's atmosphere. So this was actually known prior to the arrival of Cassini, that there are large methane storms on Titan. And it's something that I actually worked on when I was an undergrad. But from the spacecraft, we've been able to characterize them in more detail and at higher resolution. And this is a actually fairly small storm that occurred at the South Pole. And so we know and have been able to learn more about storms on Titan. We know that there's rain that's probably composed mostly of methane, although occasionally some ethane. There's actually been evidence now seen, I think, twice of the surface actually being wet after one of these storms, and so that's something else that's interesting. So we're being able to start to understand the, we call it a hydrological cycle, although that kind of implies water. So we say sometimes methane hydrological cycle, but there's methane that cycles back and forth between the atmosphere and the surface in a way that's very similar to the way that it happens here on Earth. So the good news is that because of Voyager, we knew better what kinds of instruments to send on Cassini. And so Cassini does carry a number of instruments that are able to see the surface. And so that is what Titan's surface looks like. You can see already just from this picture that there is a diversity of different kinds of units on the surface. And so I'll talk about those a little bit. Besides just from the spacecraft, we also had the Huygens probe. And so this is an image taken from the surface by Huygens. One of the things that's most remarkable about this image is that, in fact, Huygens was not designed to return data from the surface. Because we didn't know what the surface looked like, there had been some predictions that there was a global ocean. The Huygens probe was really and truly a probe that was just meant to descend through the atmosphere. Anything that it sent back from the surface was just bonus, and so this image is one of those bonuses. And what we found out when we landed was that we seem to have landed in a dried stream bed or maybe a wash. Those rocks that you see in the image are not made out of silicate, so not rock that you would think of here on Earth. They're made either of water ice or water ice mixed with organic materials. One of the things that's very striking about these about this image, about these pebbles, is that they're rounded, and so right away that tells us that they have undergone some kind of erosional processes that has resulted in them being rounded. One thing to point out about this picture is that those ones that are kind of in the foreground of the image, they really are pebbles. They're about a centimeter in diameter. They're just really, really close to the camera, and so that's why they look so big. So we now know from Huygens and from some other measurements that the surface is probably mostly water ice, bedrock, maybe some ammonia, some other organic materials. Cassini also carries a radar instrument, and the radar isn't affected at all by the atmosphere or by the haze. And so most of the best information that we've been able to get about the surface has come from the radar instrument. So this is a radar swath, a set of radar data from Titan's North Pole. And you can see right away that there are large lakes, there are extensive stream structures. In Titan's North Pole, these lakes are made mostly out of methane, ethane, and then some other materials that are dissolved in them that are also produced in the atmosphere. That largest lake, the one on the left, is called Kraken Mare. Its diameter is about 1,000 kilometers, and so these are very substantial bodies of liquid. I'll show a comparison in a couple of slides to some bodies of liquid on Earth. So the lakes are actually one of the places that we're most interested in studying for a couple of reasons. So one of the things that's interesting about the lakes is they can actually act to potentially drive further chemistry from what was happening in the atmosphere, because things that are soluble in methane and ethane, which are the main components of the lakes, will dissolve. But things that aren't soluble will end up as sediment on the bottom of the lake, and the bottom of the lake is almost certainly water ice. And so you, from this the solubility, you fractionate things that were produced in the atmosphere, and then you put some of those materials in contact with water ice, which has oxygen, and as I mentioned, there's not a lot of oxygen in Titan's atmosphere, and so there's the potential for some really interesting chemistry. And of course, we also know from life on Earth that liquid seems to be really important for life to exist. And this is the only, these are the only bodies of liquid currently present on the surface of any body in our solar system. And so that's another reason why we think that the lakes are so interesting. The large, darker regions that you saw on that big image of Titan are dune fields, huge dune fields, very analogous to dune fields that are seen on Earth. I can't remember if I have a picture to show you that comparison or not. We'll just have to see. It'll be an adventure. But one thing, again, to remember is that the sand particles that make up these dunes are not silicate sand. So this is not sand like we're used to on Earth. We know from some of the radar measurements that the material that the dunes are made out of is most likely organic or water ice that's covered in organic. And so these are extensive dune fields that are made out of organic materials rather than rock, which again is bizarre but very interesting. Finally, one other area of Titan that we're kind of interested in for chemistry are impact craters. So Titan doesn't have very many impact craters. I think there's 6 that have been confirmed so far. And impact craters are really interesting when we study things in the solar system because it gives us a sense of the age of the surface. So if you look at the Earth-Moon system, for example, we know that the Moon is just covered and covered and covered in craters, just absolutely saturated in craters, whereas the Earth is not. But we know that the Earth and the Moon are about the same age, and so what that tells us about the surfaces is kind of 2 things. One, that the surface of the Moon must be much older than the surface of the Earth, and the reason for that is that the number of impacts that have occurred over solar system history has decreased over time. And so things that are really old have a lot of craters. And then the other thing that we learn is that Earth has a lot of erosional processes that are occurring, and so there are lots of things that act to erase any craters that are on Earth's surface, things like wind and water weather down the rocks and can erase a visible record of a crater. And so when we see that there are very few craters on Titan's surface, that also tells us that it's like Earth in the sense that the surface is probably relatively young compared to a lot of other bodies in the solar system, even other bodies in the Saturn system, and that there are processes that act to erode craters on the surface. But craters are particularly interesting because when an impactor comes in and forms a crater, it heats up the water ice and will melt it. And then the top of that pool of water will freeze over very rapidly because it is so cold. But then that kind of acts to insulate the rest of the water. And so you can actually have pools of liquid water on the surface for tens of thousands of years. And meanwhile, you also have all these organic materials that came from the atmosphere that are now exposed to liquid water. And so that turns out to actually be a really interesting chemical environment too, because once the water interacts with these organic materials and does what we call hydrolyze them, we can get a lot of other kinds of molecules that we didn't have before. So things like alcohols, acids, maybe even amino acids. Amino acids are the building blocks of protein for all of life on Earth. And so this is another area that might be really interesting. Because we could have further chemistry going on the surface. So that's just kind of a quick summary of some of the things that we've learned about Titan from Cassini. I'm just going to step through a couple of mostly just gratuitous pretty pictures so that I can show you some of the other cool things. This is an image that was taken from Huygens before it huygens on the surface. So Huygens kind of ended up at the bottom right of that picture. But we can also see stream channels from the Huygens image, and it turns out that that area, the kind of brighter area at the top of the image, is higher than the area at the bottom, and so it looks as if those stream channels feed into kind of a larger wash area at the bottom. One of the things that I think is super interesting about this image is that when they took radar measurements of this area, the resolution of the radar is not good enough to actually see the streams. So the picture I showed you before of the radar, you could really see those streams and rivers at the North Pole, but you can't see them at the Huygens landing site, even though we know they're there. So that means it's possible that large areas of Titan are covered in these channels and that we just haven't been able to see them because we can't see them in the radar. The resolution's not good enough, and we haven't been able to image the rest of the planet as close up as we were able to at the Huygens landing site. So it's possible that just the whole body is covered in these extensive stream channels. This is probably my favorite picture from Cassini. I don't know, you all probably saw there was a big to-do last week. I meant to put it in and I forgot about this this picture of Saturn that Cassini took when we were all supposed to be waving at the spacecraft when it took the picture, since Earth is one of the bodies that's also in the image. So Cassini has returned these really spectacular images of the Saturn system, but I think this one's still my favorite. And this actually wasn't taken by the camera, which is where our pretty pictures usually come from. This is an image that was taken by an instrument called VIMS. It's a visible and infrared mapping spectrometer, which is meant to be looking at the composition mostly of surfaces of the icy bodies in the Saturn system. But what they managed to catch here, and some of you may have already figured out what this is a sun glint. So this is actually the coherent reflection of sunlight off of one of the lakes on Titan's North Pole. The lake that it was reflected off of, they were able to figure out, is a lake that they now call Jingpo Locus, and it was named that because that means mirror lake, and they wanted to call it that because they had caught this specular reflection, this sun glint. And so I just think this is one of the most amazing images. It's the first time that we've seen a sun glint off of a body of liquid anywhere else in the universe besides the sun glints on Earth. And so I always have to just show this picture because I think it's so remarkable. This is a quick comparison. I had mentioned that I would compare some of the lakes to bodies of water here on Earth. And so this is Ligeia Mare, which is one of the large seas on Titan compared to Lake Superior. And so you can see it's actually a bit bigger. So these are very large seas on Titan, and of course remembering that Titan is much smaller than Earth, smaller surface area, and so these lakes are really quite huge when you compare the fraction of area that they're covering on Titan. So now I'm going to focus more on Titan's atmosphere. Let me see how we're doing on time. Okay, so I'm going to just mention a few things about how we study Titan's atmosphere. So Titan, Cassini, as I mentioned, Cassini carries a lot of different instruments. And one of the reasons for this is that we want to do both what we call remote sensing, so we want to be able to study things from far away, but we also want to do some in situ measurements, so we actually want to be able to go, in this case, through the atmosphere and do measurements while we're there. And so this is a plot that shows the temperature is on the x-axis, and that's the solid line in the plot. And then altitude or pressure, depending on which unit you prefer, are shown on the y-axis. And I've just made a little indication of where Cassini can go. So the deepest in Titan's atmosphere Cassini can go is about 800 kilometers from the surface, 850 kilometers from the surface. And the reason for that is that Titan's atmosphere is so thick that if it went any deeper, there would be too much drag on the spacecraft. And so if it went a bit deeper, it would just it would drag a lot on the spacecraft would come out kind of not in the correct orientation or whatever. But if it went too deep, it would actually end up probably crashing into Titan, which is not ideal. So we have instruments that can do measurements when we're flying through the top of Titan's atmosphere. And so I've indicated kind of off to the side, there's a bunch of acronyms. I'll tell you what they are. So that orange box says INMS. That's the ion and neutral mass spectrometer that Cassini carries, and that can measure the gas phase composition in Titan's atmosphere when Cassini is flying through Titan's atmosphere, which it does a fair number of times. So we now, as I said, we're about almost 10 years into the mission, and we've done about 100 Titan flybys. They occur at different altitudes, and different instruments get to take measurements, and so we don't have 100 flybys worth of mass spec data, but we have a fairly substantial number at this point. And then the other boxes on the left indicate remote sensing instruments, and so these are all instruments that Cassini carries that Cassini can use to measure the composition and also temperature of Titan's atmosphere when it's kind of flying further away. And so the green box is called UVIS. That's an ultraviolet imaging spectrograph, and so it looks at ultraviolet wavelengths, and that allows it to measure the composition from about 500 kilometers to about 900 kilometers in Titan's atmosphere, and it does this by looking at either stellar occultations or solar occultations, and so the instrument looks at Titan's atmosphere when there is a star behind Titan, and so we're looking at the starlight or the stellar or the sunlight through the atmosphere, and we're looking at how the atmosphere absorbs that light to try to learn about the composition. Lower down in the atmosphere, we use an instrument called Cassini-Huygens. It's a composite infrared spectrometer, and Huygens looks at infrared light in the way analogous to that instrument I had mentioned before that was carried by Voyager. And so we can learn about the composition and temperature in that region of the atmosphere from about 100 kilometers up to about 500 kilometers from that instrument. And then the Huygens probe carried an instrument called GCMS. It's a gas chromatograph mass spectrometer. And so that instrument was able to measure the composition of Titan's atmosphere just at the very, very bottom after the parachutes had already deployed and the spacecraft was going much slower. They were able to do composition measurements on the way down. And so we only have measurements of the composition in that part of the atmosphere for one place at one period of time because of Huygens. The other instruments, we have information about different parts of the atmosphere, different latitudes from different flybys, and we also have been able to get information over time because of the length of the mission. And so we actually know a lot more about the composition of Titan's atmosphere from about 100 kilometers up than we know from that little bit down, which is unfortunate. That's a region of the that is a region of the atmosphere that's very difficult to measure from remote sensing. And then one other thing that I just wanted to point out that's on here because I had mentioned it is that we have these two different kinds of haze in Titan's atmosphere. We have this detached haze layer and the main haze layer. And so we're able to study those two things also using these instruments because they interact with light in a way that's different than the gas phase molecules do. And so from UVIS and from Cassini-Huygens, we're able to study the haze a little bit as well, although that's not really intentional. If you ask the people who analyze that data, they just tell you that the haze is a pain in the butt and it's just in their way all the time. But for those of us who are actually interested in it, that's useful information, even though it makes everyone else's life difficult. Let's see what's next. Oh, so I don't know how much longer I'm gonna talk about this. I'm gonna briefly mention two things that we've learned from Cassini that I think are really interesting that don't make good, pretty pictures. So one of the things that and these both come from an instrument called CAPS, which I didn't mention before. It's a Cassini plasma spectrometer. So one of the things, and I'm not going to do this data justice at all, the only reason I put this plot up here is because I wanted to point this out. So one of the things that CAPS has discovered is that there's O+ flowing into Titan's atmosphere. And the reason that we're so interested in this is that as I mentioned, Titan's atmosphere is actually fairly reducing, and so the fact that there's this flow of oxygen coming into Titan's atmosphere from some kind of external source turns out to be really interesting for chemistry for us. And then the other thing, which I think is actually probably one of the most amazing discoveries that has been made by Cassini, although other people might disagree, is that we've really learned a lot more about the chemical complexity of Titan's atmosphere. So I had mentioned that we knew that there were molecules that are what we call aromatic. So prior to Cassini's arrival, the heaviest molecule that had been detected in Titan's atmosphere was benzene, which is C6H6. And so that has a mass of 78. And so if you had kind of guessed what a mass spectrum of Titan's atmosphere would look like prior to Cassini's arrival, you might guess that it looks something like this. So the x-axis is the mass of the molecules that we see, and then the y-axis is just the number. And that's kind of typical for mass spec data. And so when we actually got there and started getting mass spec from CAPS, we found out that they actually look like this. So one thing to point out right away is that the x-axis is logarithmic in this plot, which is actually really atypical when you show mass spec data. So it turns out that there's molecules that actually have a mass of up to 10,000 AMU that have been detected in Titan's atmosphere, which is rather than 78, which was kind of what we thought we might expect, which is 6 carbon atoms. 10,000 AMU is something more like 700 or 800 carbon atoms. And I couldn't even really fathom what this would mean, and so I drew some pictures. So this is what benzene looks like with its little ring and its 6 carbons. So then I drew a molecule that has a mass of 10,000 AMU, and that's what it looks like. So this is just to show you that we were, our understanding of Titan's atmosphere was really, really wrong, is really what to emphasize more than anything. And so this has kind of really fundamentally changed our ideas about how haze forms in Titan's atmosphere, because prior to Cassini's arrival, we really thought that the haze formed where we see it, which was much lower in the atmosphere. Remember, I showed that the detached haze layer is, around 500 kilometers in the atmosphere, and the main haze layer is much deeper, maybe around 300 kilometers to the surface. And we kind of thought that the chemistry was happening where we saw the haze. But now we know that these ions exist very high. So this is at an altitude of about 1,000 kilometers, the set of measurements I'm showing here. And so that really means that the chemistry is starting much higher up in the atmosphere. And that has a lot of really interesting implications in terms of understanding haze formation in Titan's atmosphere, and also just understanding haze formation in atmospheres in general, because the pressure is very, very low in this region of the atmosphere. And so we say, the mean free path, so the distance between each collision that a molecule undergoes in this region of the atmosphere is a couple of kilometers. And so a molecule has to travel a few kilometers before it even has the possibility of running into another molecule. And whether or not it's going to react is a whole other issue. And so we're still trying to understand how you can go about building a molecule that is this huge when your molecules barely even ever run into each other and have the possibility to react. So this is, as I had mentioned, really changed our understanding of haze formation in Titan's atmosphere. So let's see. I don't know what else is on here. Maybe nothing. Oh, there we go. So one thing that I do want to mention is just to kind of give you a sense of why we care about haze. So there's a lot of different reasons why haze is important in planetary atmospheres, both our own and other atmospheres. So there's things that are kind of practical considerations. So I had mentioned that some of the instrument teams kind of hate haze because it gets in their way. So because haze absorbs and scatters light, it is present in any kind of remote sensing measurements that we do. And so to be able to understand the measurements when we're looking at gas phase composition or when we're looking at temperature, we also have to be able to remove the signal of the haze. And to do that, we have to know something about it. And this is important not just for Titan, but also we're starting to look at measuring the composition of extrasolar planet atmospheres. And it seems like a lot of those atmospheres have some kind of haze or clouds in them as well. It also affects the radiation budget of an atmosphere and a surface. So particles absorb and scatter light much differently than gases do. And so this really can change the way that solar radiation, for example, is transported through an atmosphere. And so it's something that's really important because it can change the temperature structure of an atmosphere, and it can also change the surface temperature on a planet. And so that can have implications for whether or not a planet is habitable. And usually when we say that word, we just mean whether or not liquid water can be present on the surface. And this is also something that's really important even for Earth. So the most recent Intergovernmental Panel on Climate Change report just came out, the IPCC, and they have this great plot. I should really put it in here, but they have a plot that shows all the different pieces of information that you put into a climate model and how much those things affect the temperature here on Earth, and then they also give an indication of how certain we are about those effects. And hands down, the largest source of error in climate models is our understanding of aerosols and the way that they affect radiation in an atmosphere. And so you can imagine if we're having trouble getting that information here on Earth, where we have access to all of those things and we can study them in lots of different ways, you can imagine that it would be really difficult to get that information for places where we don't have the ability to get so much information. So this is another reason why we care about it. One of the other things that's interesting about haze that I had kind of alluded to before is that depending on the kind of haze, it can also provide a source of organic material to a surface. And so in Titan's atmosphere, for example, there is so much complex organic chemistry occurring in the atmosphere. And those organic molecules eventually end up on the surface. And so one of the reasons that we're interested in studying this kind of haze is to try to figure out what kinds of molecules haze might provide to either be materials available for the origin of life or materials available for evolution of life kind of at the beginning. And so one of the things that I like to say is that one of the questions that I'm most interested in is trying to understand how far organic chemistry can proceed in the absence of life. And further than that, I'm interested in trying to understand how far organic chemistry can proceed in the absence of life in an atmosphere. And so one of the questions that I'm really interested in answering is, how complex of molecules can we make in an atmosphere? Can we make amino acids, which are the building blocks of protein? Can we make nucleotide bases, which are the building blocks of DNA on life on Earth? Or, could we build a protein? I mean, what's the most complex kind of molecule that we can make in an atmosphere? And this is, again, goes back to the plot I was just showing, that our answer to that question has really changed quite drastically over the last few years because of Cassini. It used to seem ridiculous to even say that it might be possible for an atmosphere to make something like a protein. But now these molecules that we're seeing in Titan's atmosphere are heavy enough that, that is the mass of a small protein. And so this is one of the other things that we're interested in. And finally, the other reason that we care about haze, or at least why I care about haze, is that haze contains a record of atmospheric processes. And so what I mean by that is that, now that we know that haze formation starts very high in Titan's atmosphere, so starts basically at the very top of Titan's atmosphere, that means that if we were able to go to the surface and, scoop up some of the material that had rained out of the atmosphere, we would hold in our hands a record of the entire atmosphere, because the haze experienced the entire atmosphere. And so we would have a record of every energy environment, every temperature environment, every pressure, every composition, every other kind of process, dynamics, condensation, all of these different things would have happened to that haze particle. And so it's up to us to be smart enough, basically, to be clever enough to figure out how to extract that information from the haze particles themselves. And of course, that's the tricky part. It's easy to say that the record's there. It's hard to actually be able to pull it out. And so my PhD advisor likes to joke that one of the things that we're interested in figuring out is haze archaeology, which I think is kind of a fun way to describe it. I don't know, how am I doing on time? I can keep talking, or people can ask questions. It's up to you guys.
Wrap it up.
If you could wrap it up, that'd be great.
You're muted. Oh, you're unmuted.
Then we can just do questions.
Okay. Does anybody have any questions from any of the other locations on Google Hangout?
Turn off the block.
They mute themselves.
Oh, they unblock.
So if you don't have any questions, do we have any questions for her?
I have one.
Okay.
Go for it, John.
How does the average temperature on Titan compare to the other moons?
That's a really, really good question. So it's something that I didn't mention, and it's super interesting. Titan's atmosphere has actually about a 20 Kelvin greenhouse that comes from a combination of the methane in Titan's atmosphere. Methane is a very good greenhouse gas, and also the haze layer. And so the surface temperature would be about 20 Kelvin colder if it weren't for the atmosphere. And so that means that the rest of the moons in the Saturn system are about 75 Kelvin, depending on the moon. One of the other things that's actually super interesting about that is the methane is actually responsible for the fact that Titan has an atmosphere at all. If Titan's temperature was 75 Kelvin, that's actually too cold for nitrogen to exist as a gas. And so if the methane wasn't present, the entire atmosphere would collapse out. And that's probably something that will happen in the future. It may also have been something that happened in Titan's past as well. And so it's possible that Titan has kind of a cyclic atmosphere, and that it goes back and forth between collapsing out and then reforming again. That's something that we're still interested in studying. But it is actually warmer than the rest of the Saturn system, believe it or not.
I believe it.
Does anybody else have a question?
What is the rotational period, and how does that affect temperature?
Of Titan? rotational period of Titan. Anybody hear me? So Titan's actually tidally locked, just like Earth's moon. And so Titan always has the same side facing the sun. And it orbits, I forget exactly what the orbital period is. It's on the order of an Earth day, maybe even a little bit less. So I'm not sure what the origin of that question was, but it's tidally locked, as are almost all of the moons in our solar system. Actually, when you are a little guy orbiting a big guy, eventually you end up tidally locked.
I was asking that because the one side facing the sun would heat up more than the other.
I'm sorry?
The side facing the sun, if
Uh-huh.
it faces the sun all the time, then that side would be at least significantly warmer than the other side.
Right, okay. So the thing is that there's actually very little day to night temperature variation on Titan. It's actually very difficult to detect. So it's on the order, it's actually about less than a degree. So because Titan's atmosphere is so thick, it has a really high thermal inertia. And so the day to night temperature variations pretty much just actually wash out because of that. And it has a very, very small equator to pole variation also, even though it does have quite a bit of an axial tilt. It's pretty similar to Earth, actually, in that respect. So it has substantial seasons, but the equator to pole temperature variation is very small as well. It's only a few degrees, and the main reason for that, again, is just you have this very thick atmosphere that has a really high thermal inertia.
Okay.
Does anybody else have any questions?
I have a question. So talking about the instrumentation and how if the funding doesn't continue that you won't be able to keep up with the project, I was just wondering what the funding actually covers.
So right now, and Cassini isn't the only mission in this boat right now. Cassini is currently, I think, in its 3rd extended mission. So when NASA sends spacecraft wherever we go in the solar system, or even Earth spacecraft, you have what we call a nominal mission. And so basically that's how long you need to achieve the science goals that you have set forth. And so basically you go to NASA and you say, here's my science goals, here's how long the mission will take to achieve those science goals, here's how much this whole thing is going to cost, and then NASA says, okay, cool, go do this. I mean, normally they tell you to go jump off a cliff, but occasionally they say, okay, cool, go do this. But what ends up happening almost all the time is that the engineers who build these things are so amazing that the spacecraft just last forever. And so you can think of, for example, the Mars exploration rovers, which landed in 2004, were meant to spend 3 months exploring Mars, and Opportunity is still driving. That was almost 10 years ago. So in that case, what you do is you get to the end of your nominal mission and you go back to NASA and you say, hey, look, my spacecraft is awesome and we're doing awesome science, and look at all this other really awesome science we can do if you give us more money. And the vast majority of the time, NASA says, okay, here, you can have more money. So Cassini's in its 3rd extended mission right now. The Opportunity rover I had mentioned is an extended mission. There's a spacecraft at Mercury right now called Messenger. That's an extended mission. The Mars Reconnaissance Orbiter, which is an orbit around Mars, is an extended mission. Even Curiosity, the rover that landed on Mars last year, is currently just starting its 2nd year of operations. And at the end of that 2nd year, it will also go into extended mission. And so basically every year, every couple years, NASA sits down and they say, okay, how much money do we have for extended missions? And then based on that, which missions can we keep funding? So the situation right now is that there's not enough money for all of the extended missions starting next year. I think I might cry. So right now, Cassini costs about $50 million a year to operate. And most of that money actually goes towards planning. So as I mentioned, there's a number of different instruments on the spacecraft, and each one of those instruments has to have all of its observations planned. This requires a lot of different people. There's also the money that goes towards getting the data analyzed. It costs money to send the data back it's not cheap. Like if you think going to Europe and accidentally leaving your cell phone on costs a lot of money, you would not believe how much money it costs to send data back from Saturn. And so we're about $50 million. The only other mission that is that amount of money in extended mission is Curiosity, the Mars rover. All of the other missions are less money than that. And so it looks like what's probably going to happen is that they're going to have to make a decision between Curiosity and Cassini, and that depends entirely on whether or not NASA is able to get more money for the extended missions. And the consensus kind of is, although I obviously probably don't agree, that if it comes to that, if it comes to the decision between Curiosity and Cassini, that they will choose Curiosity, because Curiosity is still kind of a baby spacecraft. She's only been driving around Mars for a year. By the time that this decision would go into effect, she'll only have been there for 2 years, whereas Cassini has been there, as I mentioned, for 10 years and has already done a lot of really amazing science. So that decision is coming up fairly soon, actually, so anybody who is so inclined, if you wanted to contact your representatives or the president and tell them that it would be super duper awesome if they could find what amounts to pretty much zero money in the federal budget to fund all of the extended missions that NASA is currently looking at, that would be really great. The last couple years of Cassini are going to be amazing. Cassini is going to start doing what we call the proximal orbits, and so they have been very, very careful to keep the spacecraft as far away from the rings as possible, with the exception of the engine burn that put Cassini into orbit. They have stayed as far away from the rings as they can because Cassini is traveling very fast, and running into a ring particle at that speed would be very detrimental to the spacecraft. But since we're crashing the spacecraft into Saturn anyway, it doesn't matter towards the end. And so they will first do a set of orbits outside of the rings, but very close to them, to try to learn more about the rings. We actually don't know very much about what the rings are made of or where they came from. And finally, the very end of the mission, they'll do a set of, I think, 20 orbits inside of the rings. And so they'll be orbiting between Saturn and the rings, and they'll start to be able to do measurements of Saturn's atmosphere and all kinds of science that the mission was not designed for, and all kinds of science that we can't get any other way. And so it's going to be a really big shame. I think this may sound like an exaggeration to some people, but really a loss for humankind in terms of learning more about the universe that we live in. If we can't find that money to be able to do the extended mission. That was a very long answer to your question, sorry.
No, that's a good answer. Yeah.
All right. Does anybody else have any questions? I'd like to wrap it up.
Well, if you give some advice to these undergraduates, what would you tell yourself if you could talk backwards in time?
Okay, there's like practical things, and then there's like cheesy life things. So I guess the practical things are that if you want to do anything to do with science or engineering, it is to your benefit to, as soon as possible, learn to communicate, both written and speaking. I spend an absurd amount of time writing every day, or at least I should. Some days I don't. Learning how to program will serve you well no matter what it is that you do. And the more languages that you're at least comfortable with and familiar with, the better you are. So those are kind of the practical things. And then I guess the cheesy thing is to do the thing that makes you happy, and to not let anybody tell you that you can't. And so there are things that might seem ridiculous to you, but you have to go for them if that's what you want. And it might not happen, but it'll certainly never happen if you don't try. And so, don't let the inner voice or even outer voices tell you not to do something. Go for it, and if it doesn't happen, at least you tried.
Cool.
All right. We'd like to...
Very awesome.
Oh no.
Okay,
Is there a mouse?
so I'm going to stop the broadcast, but you'll still